Okay, let's start. A real-life interrupt handler. Let's look at a real interrupt handler from the real-time clock RTC driver found in drivers char rtc.c. An RTC is found in many machines, including PCs. It is a device separate from the system timer, which sets the system clock, provides an alarm, or supplies a periodic timer. So if you don't know what an RTC looks like, RTC computer, it looks like this. It looks like one of these like button cell things on your. If you ever open up your computer, it looks kind of like that. There's also variations where they kind of look like this big black chip here. But yeah, most of the times it'll look like these button cells. So oh yeah, so what's inside these big chips are just button cells in turn themselves. So a lot of people have actually opened them up and replaced the the battery that way too. So yeah, these batteries help keep track. Like when your computer's off, it helps keep like the clock ticking essentially. Anyway, on most architectures, the system clock is set by writing the desired time into a specific register or I/O range. Any alarm or periodic timer functionality is normally implemented via interrupt. The interrupt is equivalent to a real-world clock alarm. The receipt of the interrupt is analogous to a buzzing alarm. So every once in a while, the RTC is going to interrupt the system. So when the RTC driver loads, the function RTC init is invoked to initialize the driver. One of its duties is to register the interrupt handler. So this is inside RTC.c. We have this one here where it calls request RQ, which is going to register this RTC interrupt handler to the RTC interrupt line. It's shared and its name is RTC, and this is basically the dev cookie that's used to reference back to this specific interrupt handler. This specific interrupt handler within this interrupt line. In this example, the interrupt line is stored in RTC IRQ. This variable is set to the RTC interrupt for a given architecture. On a PC, the RTC is located at RQ8. The second parameter is the interrupt handler, RTC interrupt, which is willing to share the interrupt line with other handlers thanks to the IRQF shared flag. From the fourth parameter, you can see that the driver name is RTC. Because this device shares the interrupt line, it passes a unique per device value for dev. Okay, so if we look at again our shell here, we can do cat proc interrupts, and if we go to interrupt 8, for example, let's scroll up. Yeah, interrupt line 8, we see that we have a device named RTC0. So this is actually the name that gets passed for our system. So okay, so here's what the interrupt handler looks like for this specific RTC interrupt line. This is the function that gets registered in the request underscore IRQ function. So basically it acquires a spin lock, and then it does, I guess it just increments things, and then it just unlocks, and then it does more stuff here, and then it returns IRQ handle. Remember, there's like two values that get returned in interrupt handler. It's going to be IRQ underscore none or IRQ underscore handle. Okay, so this function is invoked whenever the machine receives the RTC interrupt. First, note the spin lock calls. So the spin lock calls here. Okay. The first set ensures that RTC IRQ data is not accessed concurrently by another processor or an SMP machine. So basically, there's a chance that another core, and like let's say you had like a 4-core CPU, if one of the CPU cores is handling an interrupt related to the RTC, these locks exist here so that any other cores don't inadvertently start handling this stuff here. So yeah, well, not handling this stuff, but accessing this RTC IRQ data. And this RTC IRQ data is coming, I guess, from a global declaration. Yeah. Okay. And the second set protects the RTC callback from the same thing. Okay. Locks are discussed in Chapter 10, Kernel Synchronization Methods. The RTC IRQ data variable is an unsigned long that stores information about the RTC and is updated on each interrupt to reflect the status of the interrupt. Next, if an RTC periodic timer is set, it is updated via mod timer. Okay. Timers are discussed in Chapter 11, Timers and Time Management. So, meaning, let's not worry about that for now. Okay, finally. The final bunch of code under the comment "now do the rest of the actions" executes a possible preset callback function. The RTC driver enables a callback function to be registered and executed on each RTC interrupt. So basically, you can actually tell it to execute. Oh, geez. You could always tell the RTC handler, the interrupt handler, to execute a custom callback when the interrupt occurs too. So you can register your own custom callback here. RTC callback. Okay. Finally, this function returns IRQ handled to signify that it is properly handled this device. Because the interrupt handler does not support sharing, there is no mechanism for the RTC to detect a spurious interrupt. This handler always returns IRQ handled. Interrupt context. So remember, we had a process context whenever system call occurs, and whenever interrupt occurs, we have an interrupt context in which the kernel runs in. So when executing an interrupt handler, the kernel is an interrupt context. Recall that process context is the mode of operation the kernel is in while it is executing on behalf of a process. For example, executing a system call or running a kernel thread. In process context, the current macro points the current macro points to the associated task. Furthermore, because a process is coupled to the kernel in process context can sleep or otherwise invoke the scheduler. Interrupt context, on the other hand, is not associated with the process. So another important detail, remember, interrupt context is not associated with a process. So therefore, the current macro is not relevant. It just points to the interrupted process. It doesn't mean that the kernel is executing for this process. It just means that when the interrupt occurs, when a process is running, current is going to point to that process that was interrupted. But I guess the book is saying that's not particularly useful here. Without a backing process, interrupt context cannot sleep. How would it ever reschedule? Therefore, you cannot call certain functions from interrupt context. If a function sleeps, you cannot use it from your interrupt handler. This limits the functions that one can call from an interrupt handler. Interrupt context is time critical because the interrupt handler interrupts other code. So remember, this discussion we've been having right now with interrupts and interrupt handlers have always been in the context of the top half of like the interrupt flow. So basically, the time critical things, the things that need to be finished quickly so that the kernel can move on to doing other things. Okay, so the code should be quick and simple. Busy looping is possible, but discouraged. This is an important point. Always keep in mind that your interrupt handler has interrupted other code. So always keep in mind, like, that's the reason. One of the other reasons why your interrupt handler should run quickly is because it is interrupting other code that was running before. And it could possibly even be another interrupt handler on a different line. So on a different device, you could have been interrupting. Because of this asynchronous nature, it is imperative that all interrupt handlers be as quick and as simple as possible. As much as possible, work should be pushed out from the interrupt handler and performed in the bottom half, which runs at a more convenient time. The setup of again, one thing to keep in mind is that, like, yes, an interrupt handler can interrupt another interrupt, because as long as that interrupt is on a different line, it is possible. The only time it's not possible is you cannot have another interrupt coming in on that same interrupt line. But for all other interrupt lines, that is totally possible to happen. Okay, so the setup of an interrupt handler stacks is a configuration option. Historically, interrupt handlers did not receive their own stacks. Instead, they would share the stack of the process they interrupted. The kernel stack is 2 pages in size. Typically, that is 8 kilobytes on 32-bit architectures, and 16 kilobytes on 64-bit 64-bit architectures. Because in this setup, interrupt handlers share the stack. They must be exceptionally frugal with what they allocate there. Whoa. Okay, wait, let's read this again. Okay. So the kernel stack is 2 pages in size. So the kernel stack is only 2 pages in size. So let's just say it's 16 kilobytes. So because in this setup, interrupt handlers share the stack. So all interrupt handlers are sharing the same kernel stack, which is only 16 kilobytes. So you have a lot of interrupt handlers. They are sharing just only 16 kilobytes on stack. So you have to be very careful with the data that you allocate in that stack. So you can't just allocate like arrays that are 1,000 elements in length, because you're taking away memory, stack memory, from another interrupt handler potentially, and you could cause like a stack overflow in this case. And this is my understanding of reading this paragraph. So of course the kernel stack is limited to begin with, so all kernel code should be cautious. Early in the 2.6 kernel process, an option was added to reduce the stack size from 2 pages down to 1, providing only a 4 kilobyte stack on 32-bit systems. This reduced memory pressure because every process on the system previously needed 2 pages of contiguous non-swappable kernel memory. To cope with the reduced stack size, interrupt handlers were given their own stack, 1 stack per processor, 1 page in size. Okay. So now interrupt handlers were given their own stack. Okay, so now if you turn on an option in the 2.6 kernel, and I guess above, you can allow each interrupt handler to get their own kernel stack that's only 8 kilobytes in size in 64-bit systems. So this is probably the default option, I guess. And then this one is an option you can turn on. So one shares all. The other one will only have their own, but it's only 1 page size. So, okay. 1 page in size. This stack is referred to as an interrupt stack. So it's no longer called the kernel stack here. It's called the interrupt stack. Although the total size of the interrupt stack is half of that original share stack, the average stack space available is greater because interrupt handlers get the full page of memory to themselves. So now each individual interrupt handler gets their own page. I think that's better. Yeah. Your interrupt handler should not care what stack setup is in use or what the size of the kernel stack is. Just always use the absolute minimum amount of stack space. So that's just like a good guidance, dude. Like you shouldn't really care. If you always try to be a good citizen, it doesn't matter. So how to implement interrupt handlers? Perhaps not surprising, the implementation of the interrupt handling system in Linux is architecture dependent, meaning that how you implement interrupts just depends on what type of CPU architecture your kernel is going to be running in. The implementation depends on the processor, the type of interrupt controller used, and the design of the architecture and machine. So figure 7.1 is a diagram of the path an interrupt takes through hardware and the kernel. So basically you have, let me see if I can do this. Let's see if I can take a picture. How do I take a picture of this thing? Oh, I can't anymore, huh? Let's see. I need flame shot. Okay, let's do it. Flatpak. I think I can install Flatpak on Arch. Let's do this. Sudo pacman sy Flatpak. Oops. I want to take a screenshot of this and mark it up. I might as well just install it anyway, so that you know. Okay. And then so that's installed, and now I just need to install flame shots. Let me add the repo to run Arch. So install some apps. Let's do flame shot. here. Oh. Of course, installing anything NVIDIA is going to be risky. Should really just stick in my AMD card. I have one, so. But this computer is already kind of Frankensteined as it is already. Out of a bunch of spare old parts. Okay. Now let's do this. Flame shot. So no flame shot. Okay, let's just run it manually. I think I need to restart my computer, but I have no time for that. So, boom. Okay. So let's do this. Okay, let's just do that. And then I don't even know why I'm doing this. It just seems cool, and I need to set this up anyway properly. Okay, let me see if I can just resize that. Okay, cool. So going back to what we were doing before. Okay, so this is physical, right? This is coming from the user typing. Right, types. Now, what ends up happening is that when you're typing, the keyboard has a little chip inside, right? Called the microcontroller. Inside the keyboard, okay? That actually generates an interrupt. This here, okay, is actually hardware. It's in like your computer, and it sends signals to your CPU to interrupt the processor. Now the processor gets interrupted, and then it halts the kernel for a moment. And in the kernel code, so at this point, all of this is kernel code. Okay, the kernel is actually going to execute this function, do_IRQ here. Do_IRQ is going to, I think, loop through every single interrupt line and check to see if there is actually an interrupt in that line. And so if there is, it's going to just handle the interrupt by looping. Remember, this is going to be going through each single interrupt handler. So we call them ISRs, right? Going through each one of them and executing or finding whether or not they're executable, if they relate to that interrupt line. If so, it'll run it and it'll just return, right? And it just does this repeatedly until there's no more interrupts, and then it just returns back. Okay, and so that's the flow. So this do_IRQ here is like the main entry point to interrupts, and I think we could find that somewhere here if we were to grep. Oops. So do_IRQ. Okay, I think it's just something like that. So I think it's just, it's this one right here. Yeah. So this one is do_IRQ for what? Yeah. Do_IRQ is deprecated. Please convert the proper flow handlers. Whatever. This is the original, which is used for every interrupt type. Sure. Let's just assume. Okay, let's just do this. Or let's just find the other one. You figure all this would be cached. No, I think that's it. Oh, wait. Oh, they're architecture specific now. Okay. Makes sense. So there should be a x86 one somewhere. Wow. Right here. This one. Arch x86. So this one. This is the real one. So this is actually the one that will handle, see like what the comment says, do IRQ handles all normal devices IRQs. And then notice how, let's see here. So IRQ entry, set IRQ regs. Okay, so it handles a specific IRQ here. So do IRQ actually takes in, I guess, the register information to determine exactly which interrupt handler to execute. And I think this regs is actually the, was that like the dev? So we go here to handle IRQ. Oh man, we gotta go up and look at it. So it's probably somewhere in interrupt.h most likely. So, but anyway, that's where it is. I think that's do IRQ. So handles all normal devices IRQs. Okay, so yeah. Okay. Oh yeah, no, it's true. Yeah, so it takes the registers and then it checks to see if there's a interrupt, and then it'll basically handle IRQ event. So that is handle IRQ right here with the specific IRQ line. Yeah, that looks about right. Get CPU vector IRQ. Sure. So a device issues an interrupt by sending an electrical signal over its bus to the interrupt controller. If the interrupt line is enabled, they can be masked out. The interrupt controller sends the interrupt to the processor. In most architectures, this is accomplished by an electrical signal sent over a special pin to the processor. Unless interrupts are disabled in the processor, which can also happen, the processor immediately stops what it is doing, disables the interrupt system, and jumps to the predefined location in memory and executes the code located there. This predefined point is set up by the kernel and is the entry point for interrupt handlers. Okay, the predefined point is set up by the kernel and it's the entry point for the interrupt handlers. The interrupt's journey in the kernel begins at this predefined entry point, just as system calls enter the kernel through a predefined exception handler. For each interrupt line, the processor jumps to a unique location in memory and executes the code located there. In this manner, the kernel knows the IRQ number of the incoming interrupt. Okay, so the kernel knows that. The initial entry point simply saves this value and stores the current register values, which belong to the interrupted task on the stack. Then the kernel calls do IRQ. From here on, most of the interrupt handling code is written in C. However, it is still architecture dependent. Right here, the do IRQ function is declared as unsigned int do IRQ struct pt reg. So this is what we saw right here. Because the C calling convention places function arguments at the top of the stack, the ptreg structure contains the initial register values that were previously saved in the assembly entry routine. So these were the registers before we're going to muck up the stack, I guess. Let's see, because the interrupt value was also saved, do IRQ can extract it. After the interrupt line is calculated, do IRQ acknowledges the receipt of the interrupt and disables interrupt delivery on the line. So let's see. IRQ enter. Okay. So old reg is right here. So it's temporarily holding that. And so that it's because it's going to mess everything up. Well, not really mess, but modify it. And then it's going to enter in. It's going to call IRQ enter. And I think that does all the setup. And then it'll, handle IRQ. And then it'll call IRQ exit. And then it'll restore back the registers back to where it was before it was the CPU was interrupted by the hardware. So, see. On normal PC machines, these operations are handled by mask and ACK 8259A. Okay. Next, do IRQ ensures that a valid handler is registered on the line and that is enabled and currently not executing. If so, it calls handle IRQ event defined in kernel IRQ handler.c. Oh, okay, we should have just went there to run the installed interrupt handlers from the line. So this is the implementation. Okay, so what is it doing? Basically what? Oh, right here. Here is the interrupt handler. And here's the dev. Here's the IRQ line. Okay? And I'm guessing these are trace points. Okay, and here's the return value if it is wake thread or handled or default. Okay. While there is something to run. Sure. So if it's handled, then this just basically sets some flags. Okay. And then wake is probably something else for scheduling. Let's see. IRQ wake thread. Set the result to handle so the spurious check does not trigger. I'm guessing this is if your interrupt handler was preempted, I guess. Okay. First, because the processor disabled interrupts, they are turned back on unless IRQF disabled was specified during the handler's registration. Recall that IRQF disabled specifies that the handler must be run with interrupts disabled. Next, each potential handler is executed in a loop. If this line is not shared, the loop terminates after the first iteration. Okay, cool. So this loop is trying to execute all the handlers on that same interrupt line. Okay. So do all this, and I bet you action gets reassigned somewhere then. Yeah, action is action next, because that was like a little linked list. Okay. So when action becomes null, this exits out. And action represents the interrupt handler within that IRQ line. Okay, cool. Yeah, so otherwise all handlers are executed. After that, add interrupt randomness is called if the IRQF sample random was specified during registration. I think that is here. Okay. This function uses the timing of the interrupt to generate entropy for the random number generator. Finally, interrupts are again disabled. Do IRQ expects them still to be off. And the function returns back. Wait, so we again disabled? Local IRQ disabled. Oh, okay. Local, and then do we enable it here? Okay. Oh, yeah, because of this IRQF disabled flag. Okay. So, sure. Back in doIRQ, the function cleans up and returns the initial entry point, which then jumps to ret from interrupt. The routine ret from interrupt is as with the initial entry code written in assembly. Okay. This routine checks whether a reschedule is pending. Okay. Recall from chapter 4, process scheduling, that this implies that need reschedule set. If a reschedule is pending and the kernel is returning to user space, that is the interrupted a user process. So if a reschedule is pending and the kernel is returning to user space, so going back to the process that it had interrupted, okay, schedule is called. If the kernel is so that's to make sure that process gets back into that running state. If the kernel is returning to kernel space, that is the interrupted the kernel itself, schedule is called only if the preempt count is 0. Otherwise, it is not safe to preempt the kernel. After schedule returns, or if there is no work pending, the initial registers are restored and the kernel resumes whatever it was interrupted. On x86, the initial assembly routines are located in arch x86 kernel entry _64.s. And the C methods are located in IRQ.c. Okay, good to know. other supported architectures are similar. So this is where everything juicy is at. And I am here. So this is all the juicy stuff. Okay. Oh, we've already looked at this so many times. Proc interrupts. procfs is a virtual file system that exists only in kernel memory and is typically mounted at proc/proc. Reading or writing files in procfs invokes kernel functions and that simulate reading or writing from a real file. A relevant example is the proc interrupts file, which is populated with statistics related to interrupts on the system. Here is a sample output from a uniprocessor PC. So basically everything we've done, it looks like that. Okay. The first column is interrupt line, so we know that. And this system, the interrupts numbered 0 through 2, 4, 5, and 12, and 15 are present. Handlers are not installed on the lines not displayed. The second column is a counter of the number of interrupts received. A column is present for each processor on the system, but this machine only has one processor. As you can see, the timer interrupt has received 3,602,371 interrupts, whereas the sound card has received no interrupts. Then this is an indication that it has not been used since the machine booted. The third column is the interrupt controller handling this interrupt. XTPIC corresponds to the standard PC programmable interrupt controller. So that's the interrupt controller, XTPIC right here. So that's like the source, I guess. On systems with an IO APIC, most interrupts would listen on the IO APIC level or IO APIC edge as their interrupt controller. Finally, the last column is the device associated with this interrupt. This name is supplied by the dev name parameter to request IRQ as discussed previously. So that's the pointer to a character. If the interrupt is shared, as is the case with interrupt number 4 in this example, okay, interrupt 4 is shared with two things, Ethernet and this UHCI HCD thing. Okay. All the devices registered on the interrupt line are listed. For the curious, procfs code is located primarily in fs/proc. The function that provides proc interrupts is not surprisingly architecture dependent and named show interrupts. Okay. Interrupt control. The Linux kernel implements a family of interfaces for manipulating the state of interrupts on a machine. These interfaces enable you to disable the interrupt system for the current processor or mask out an interrupt line for the entire machine. Oh, so you can manipulate all this manually. So this it's pretty much APIs, right? Like, so these APIs allow you to disable interrupts, okay, for the CPU, or mask out, so meaning turn off an interrupt line for the entire machine. These routines are all architecture dependent and can be found in asmsystem.h and asmirq.h. See table 7.2 later in this chapter for a complete listing of the interfaces. Reasons to control the interrupt system generally boil down to needing to provide synchronization. By disabling interrupts, you can guarantee that an interrupt handler will not preempt your current code. Moreover, so let's say you have some sort of code that you don't want ever to be interrupted by an interrupt, you can disable interrupts. And that guarantees that an interrupt handler won't interrupt your code, causing it to preempt. I think that's bad practice though. So, moreover, disabling interrupts also disables kernel preemption. So it also stops the kernel from preempting stuff. Neither disabling interrupt delivery nor disabling kernel preemption provides any protection from concurrent access from another processor. However, neither disabling interrupt delivery nor disabling kernel preemption provides any protection from concurrent access from another processor. However, this is a weird sentence. Because Linux supports multiple processors, kernel code more generally needs to obtain some sort of lock to prevent another processor from accessing shared data simultaneously. These locks are often obtained in conjunction with disabling local interrupts. The lock provides protection against concurrent access from another processor, whereas disabling interrupts provides protection against concurrent access from a possible interrupt handler. Okay. Chapters 9 and 10 discuss the various problems of synchronization and their solutions. Nevertheless, understanding the kernel interrupt control interfaces is important. Okay, so this is how, okay, we saw this before, disabling and enabling. Sure. Okay, so to disable interrupts locally for the current processor and only the current processor. And I think for like multi-core systems, one core is considered to be a processor. And then later re-enable them, do the following. Local IRQ disable, then interrupts are disabled for this duration, and then you call local IRQ enable to re-enable it. These functions are usually implemented as a single assembly operation. So atomic. Of course, this depends on the architecture. Indeed, on x86, local IRQ disable is a simple CLI and local. So it's a CLI assembly instruction. So this is an x86 to clear interrupt flag. So meaning that interrupts are disabled. And then local, and this is STI, so set interrupt. So local IRQ enable is a simple STI instruction. So these are x86 instructions. So CLI and STI are the assembly calls to clear and set the allow interrupts flag. So there's a flags register in x86 that has a bit, which is a flag, that represents whether or not you allow interrupts. And these are the instructions to kind of manipulate that. Toggle them on and off. In other words, they disable and enable interrupt delivery on the issuing processor. So it is per CPU core, it seems like. Okay. So the local IRQ disable routine is dangerous if the interrupts were already disabled prior to its invocation. So if it was already disabled and then you disable again, the corresponding call to the local IRQ enable unconditionally enables interrupts, despite the fact that they were off to begin with. Okay, so if you have like a basically like this, something I think what they're trying to say is if you had called a local IRQ disable, okay, and then here's your flag, right? Let's say it starts out as 1 and you call this, then basically at that point flag becomes 0. And then if you do, I guess, and then this one is local IRQ enable, and then you're having some code here and you're working with that assumption that IRQs are now disabled. You had another, like, let's say function call where you did local IRQ disable. Okay, of course then flags will then be 0 still, but somewhere down the line you execute code and then now you call local IRQ enable. Okay, that will then flip the flags or flag to 1. Now where does that leave this code here? So this code here, okay, this code here will inadvertently will run with interrupts enabled. Bad, right? Because this was this code assumes that it should have been disabled, but this code hasn't executed yet. But the inner one had already resulted in the interrupts being enabled in this case. So I think that's what's going on. Okay. Instead, a mechanism is needed to restore interrupts to a previous state. This is a common concern because a given code path in the kernel can be reached both with and without interrupts enabled, depending on the call chain. So for example, imagine the previous code snippet is part of a larger function. Imagine this function is called by 2 other functions, one that disables interrupts and one that does not. Because it is becoming harder as a kernel grows in size and complexity to know all the code paths leading up to that function, it is much safer to save the state of the interrupt system before disabling it. Then, when you are ready to re-enable interrupt, you simply restore them back to the original state. So basically, you conditionally check like whether or not you should actually be calling this based off of the state of the system. Okay. Okay. So you do it by doing local IRQ save with the flags and local IRQ restore with the flags. So then you can do anything you want within here. So note that these methods are implemented at least in part as macros. So the flags parameter, which must be defined as an unsigned long, is seemingly passed by value. This parameter contains architecture specific data containing the state of the system. Because at least one supported architecture incorporates stack information into the value, Spark. Flags cannot be passed to another function. Because at least one supported architecture incorporates stack information into the value, so basically Spark does this differently. Flags cannot be passed to another function. Specifically, it must remain on the same stack frame. For this very reason, the call to save and the call to restore interrupts must occur in the same function. Okay, so you can't move things around because of Spark. All the previous functions can be called from both interrupt and process context. No more global CLI. Oh yeah, because CLI is all core specific. Let's read it. No more global CLI. The kernel formally provided a method to disable interrupts on all processors in the system. Furthermore, if another processor called this method, it would have to wait until interrupts were enabled before continuing. This function was named CLI, and the corresponding enable call was called STI, very x86 centric, despite existing for all architectures. These interfaces were deprecated during 2.5, and consequently all interrupt synchronization must now use a combination of local interrupt control and spin locks. And we'll find out more about spin locks in chapter 9. This means that code that previously only had to disable interrupts globally to ensure mutual exclusive access to shared data now needs to do a bit more work. Previously, driver writers could assume that CLI used in their interrupt handlers and anywhere else the shared data was accessed would provide the mutual exclusion. But the CLI call would ensure that no other interrupt handlers and thus their specific handler would run. Furthermore, if another processor entered a CLI protected region, it would not continue until the original processor exited its CLI protected region with the call to STI. Sounds like it's a deadlock, potential deadlock. Removing the global CLI has a handful of advantages. First, it forces driver writers to implement real locking. A fine-grained lock with a specific purpose is faster than a global lock, which is effectively what CLI is. So we now know that global locks are worse than local locks. Local locks because you're only locking to whatever region you're working with versus an entire system. Second, the removals streamline log code in the interrupt system and remove a bunch more. The result is simpler and easier to comprehend. Whew. Okay, so now we knew how to disable all interrupts, enable all of them, but what about for specific interrupt lines, so IRQs, right? So let's read that. Okay, so disabling a specific interrupt line. In the previous section, we looked at functions that disable all interrupt delivery for an entire processor. In some cases, it is useful to disable only a specific interrupt line for the entire system. This is called masking out an interrupt line. As an example, you might want to disable delivery of a device's interrupts before manipulating its state. Linux provides 4 interfaces for this task. So disable IRQ given some IRQ, disable IRQ no sync given some IRQ. So I'm guessing these two are more of the same, except that this has some caveat. And then this one's enable IRQ with the IRQ. So okay, that enables IRQ line. Then synchronize IRQ with that IRQ line. Okay. The first two functions disable a given interrupt line in the interrupt controller. This disables delivery of the given interrupt to all processors in the system. Okay, this disables delivery of the given interrupt to all processors in the system. So just for that interrupt. Additionally, the disable IRQ function does not return until any currently executed handler completes. Thus, Callers are assured not only that new interrupts will not be delivered on a given line, but also that any already executing handlers have exited. The function disable IRQ no sync does not wait for current handlers to complete. The function synchronize IRQ waits for a specific interrupt handler to exit if it is executing before returning. Okay. Calls to these functions nest. For each call to disable IRQ or disable IRQ no sync on a given interrupt line, a corresponding call to enable IRQ is required. Only on the last call to enable IRQ is the interrupt line actually enabled. Oh, that's cool. So there's something that keeps track. For example, if disable IRQ is called twice, the interrupt line is not actually re-enabled until the second call to enable IRQ. That's cool. All three of these functions can be called from interrupt or process context and do not sleep. If calling from interrupt context, be careful. You do not want, for example, to enable an interrupt line while you are handling it. Recall. Oh yeah. Because if you are handling a specific hardware interrupt, that interrupt line is already disabled to prevent any other interrupts from that same interrupt line from coming in. But if you inadvertently enable interrupts on that line again, you can have a lot of problems. Okay. Yeah, because recall that the interrupt line of a handler is masked out while it is being serviced. Okay. It would be rather rude to disable an interrupt line shared amongst multiple interrupt handlers. Disabling the line disables interrupt delivery for all devices on the line. So therefore, drivers for newer devices tend not to use these interfaces. Because PCI devices have to support interrupt line sharing by specifications, they should not use these interfaces at all. So PCI devices actually always install interrupt handlers to existing lines. They do share things. So I guess this is rarely used. Thus, disable IRQ and friends are found more often in drivers for older legacy devices such as the PC parallel port. Oh, okay, so this is actually not very modern. This is, okay, not common, I guess. Okay. The status of the interrupt system. It is often useful to know the state of the interrupt system. For example, whether interrupts are enabled or disabled, or whether you are currently executing an interrupt context. The macro IRQ is disabled, defined in ASM system H, returns non-zero if the interrupt system on the local processor is disabled. Otherwise, it returns 0. Two macros defined in Linux/hardirq.h provide an interface to check the kernel's current context. They are whether or not you're in interrupt and if you're in IRQ. So basically, if you are in an interrupt context, and this one is probably if you're executing an interrupt handler in that context. Let's see. The most useful is the first. It returns non-zero if the kernel is performing any type of interrupt handling. Okay, that makes sense. This includes either executing an interrupt handler or a bottom half handler. Oh, okay. Okay, so bottom half handlers, like the later stages, the async part is also considered in this call. Okay. So the macro in IRQ returns non-zero only if the kernel is specifically executing an interrupt handler. So only the top half. So more often you want to check whether or not you are in process context. That is, you want to ensure that you are not in interrupt context. This is often the case because code wants to do something that only can be done from process context, such as sleep. If in interrupt returns 0, the kernel is in process context. So non-zero means you're interrupt context. 0 means you are in process context. So yes, the names are confusing and do little to impart their meaning. Table 7.2 is a summary of the interrupt control methods and their description. Let's see. Okay, so this is everything that we discussed already. So just one thing to remember is that this one is considering both top half and bottom half. This one's only the top half, and then these right here are kind of old, like only for legacy hardware. And then this is the right way to do the interrupt disabling on CPU. This one is not the really ideal way. Okay. Conclusion. Wow, another chapter. So conclusion. This chapter looked at interrupts, a hardware resource used by devices to asynchronously signal the processor. Interrupts, in effect, are used by hardware to interrupt the operating system. Most modern hardware uses interrupts to communicate with operating systems. The device driver that manages a given piece of hardware registers in the device driver that manages a given piece of hardware, I think you should have a comma here, registers an interrupt handler to respond to and process interrupts issued from their associated hardware. Work performed in interrupts include acknowledging and resetting hardware, copying data from the device to main memory, and vice versa, processing hardware requests and sending out new hardware requests. Okay? The kernel provides interfaces for registering and unregistering interrupt handlers, disabling interrupts, masking out interrupt lines, and checking the status of the interrupt system. Table 7.2 provided an overview of many of these functions. Because interrupts interrupt other executing code, meaning processes, the kernel itself, and even other interrupt handlers, they must execute quickly, so top half again. Often, however, there's a lot of work to do. To balance the large amount of work with the need for quick execution, the kernel divides the work of processing interrupts into two halves. The interrupt handler, the top half, was discussed in this chapter, and the next chapter looks at the bottom half. Okay, so that is another chapter done. Now, just to review a little bit, just to make it clear that what we reviewed for interrupt handlers in chapter 7 was the top half portion, the part where you need to execute quickly to service the interrupt. And by executing quickly, it could mean either trying to get every work done as much as possible for that piece of hardware, or kind of setting up the system to defer it at another stage, and that stage of execution is going to be called the bottom half. So either you execute things super fast and try to get it all done in that top half, or you just do just enough to schedule the work for later to be executed at another time, and that's bottom half.